Hello, everyone, and welcome to another episode of Built on Serverless. And this time, we're going to talk a little bit about breaking the monolith. Today, my name is Ronald Widha Sunarno. I'm going to be hopefully helping you, to go through the process of breaking a monolith. But more importantly, here with us, we have Angela Wang, a solutions architect based out of Chicago. Angela, would you mind introducing yourself a little bit?
Hi, everyone. Thanks for joining us today. So I'm a solutions architect based out of Chicago. I've been working with building applications using Step Functions since it was launched reInvent 2016. And since then, I've always loved the simplicity and clarity it brings to the serverless applications. So super excited to be here today and show you how you can build a serverless app with Step Functions from scratch.
And obviously, you've done a lot of things, but one of the more exciting one that you did was creating this media process workflow reference architecture that's up on GitHub, right?
Yeah, so we can actually show you a web app that I built to demonstrate the media application. This is the use case we're going to be looking at today. So the use case is, imagine you have a photo sharing app for your users to upload their favorite cat pictures or their family photos to your photo sharing app. And you want to be able to first, when people upload these pictures, index them, make thumbnails so that you can display them on your website. You want to be able to use machine learning to automatically tag what's in the image. You want to extract metadata, things like GPS coordinates or what device made the picture. All these things are part of the kind of backend workflow that typically happens when you have a photo sharing site like this. So our topic today is how we can take a monolithic application that does image processing into a microservice-oriented distributed architecture and leverage Step Functions to help us make this process a lot easier.
That's awesome. So just kind of thinking through the steps, I would imagine since you've got a browse button there, I can click on browse, select a file, have it uploaded, and then the server-side code would do a series of steps as what you spoke about before. Extract the metadata, do some deep learning, machine learning magic, and then, it spits out all the metadata stored in the database so that we can query it from the website, right?
Exactly. So I'm showing you right now the end product of what we're trying to get to by the end of this episode. I just uploaded a picture. As you can see here, all those processing steps I mentioned earlier are happening here. We see tags that are automatically being generated. We see the GPS coordinate. We see the thumbnail that's generated by the backend processing.
Okay, so let's switch to our Cloud9 environment. For those of you who are new to Cloud9, Cloud9 is a cloud IDE hosted on the AWS services, right? And here, Angela and I are going to be sharing a Cloud9 instance. So as I'm typing, you'll be able to see the beautiful, elegant code that I have here. Obviously, awesome naming convention too. But you are actually seeing Angela's screen. So Angela has full control over what file she's going to present. But hopefully I can kind of real-time co-author a couple of basic code and contribute something to this session. So now, assuming that we want to build this app from scratch, right? So let's talk through about the different things that we want to address here. So let me start off in just kind of putting comments. The first step sounds like, based on a given image, right? Based on a given image, and I'm writing a Node.js code right here, right now. So I'm just gonna create a function that takes an image from somewhere, and probably most likely this is going to be S3, and I'm going to extract the metadata first, and then I need to figure out if, based on the metadata, is the file supported or not, right? So for example, if you upload a text file, then I probably want to reject that and stop the processing. But if it's a valid image file, then I probably want to do some deep learning inferences here. So image recognition, extract some label out, and then store it into a database, and maybe also even generate a thumbnail, right? And as you see, the example that we're talking about here is specific to media processing, but it's kind of generic, right? Like every single program that I could say, every single app that I've written in the past, I don't know, God knows, 15 years, probably looks something like this, right? A series of steps that I need to do. And, it's seemingly simple because one could just assume that I could do something like this. I would create a metadata class where the function extract given an image will return me some metadata, an array of metadata. And maybe I can have a validator class where the function is supported. When you pass on the metadata, you can kind of decide whether or not this thing is supported, right? So if validators is not supported, you can do something here, return, let's say, throw an exception. I don't know. We're just making things up as we go along. And then if assuming that it is supported, then we will probably do our magic. We would start recognizing the picture, pass on the image, and I assume this deep learning model will return us a bunch of labels, and then we would store it in the database, metadata store, pass on the labels and other stuff. And then also maybe we'll use one more class that generates the thumbnail. So in this case, most likely I'm going to be leveraging some of my custom code, right? Pull in all these classes as libraries. So let me just kind of copy paste that because I've got a bunch of library functions already on the left hand side, as you can see. Under Twitch Live, lib, I've got almighty interpreter, image processor, metadata. Those are just like code that I wrote. And in some cases, in the case of the metadata JavaScript, I even leverage image magic. So, and this is a typical monolithic code, i.e., I have to get all the functionality implemented in a single code base, have all the dependencies resolved in a single process, and then every single step of the way, I'm assuming that this is going to be somewhat procedural, step by step, right? As one step is completed, we go to the next line. But since this is JavaScript, it's not as simple as that. We want to take advantage of the asynchronous capability of JavaScript. So most likely, your code is going to look a little bit more like a chain of promises, right? So instead of extracting the image and then returning it to this variable right here, most likely this extraction is going to run asynchronously, and therefore we will get the file metadata as part of the callback. So it kind of looks a little bit like this. File meta, and then you do stuff here, right? So for those of you who are fairly new to JavaScript, all this means is just I'm calling a class that has this function called extract. I'm passing the image, and maybe this is a reference to an S3 object. And then once my extract function is done, which in this case is calling image magic and all those kind of different things, asynchronously, it's going to execute this callback upon completed. And I've got a question on the chat window. Do you use recognition for the image labels? Yes, we are. We are using recognition there. So if you look at the image, the almighty interpreter, it has a very awesome implementation of just simply calling recognition. That's the extent of my deep learning algorithmic capabilities, calling a web service function. So let's go back to the index.js again. So here, then, once I've got the metadata, I would start doing all the stuff that I was doing before. So at this point, I've got the metadata, and then if the validator is not supported, if the file metadata is not supported, then I want to return a reject, right? So that's just promises, promise.reject. And I would say here, not supported image type, let's say. And then I could, let me just fix the tabbing a little bit here. I would then also convert the next line to do the same thing. Essentially, recognize the picture, and once it's done, I'll get a bunch of labels, and then put this into here, right?
Yeah, so this is also kind of a necessary step if we want to move from a monolithic app where everything runs on the same machine to these asynchronous calls where each of these operations no longer have to happen on the same machine. So it's a network call. We make these asynchronous promises calls so that we can wait for the results to come back from the network.
Yeah.
And each of our components now can be independently scaled, and we can pick different computing platforms or run them in Lambda functions, and they don't have to all live on the same machine and share the same compute resources.
That's right. I'm just fixing some of the broken references that I have there. Metadata, store, and file meta. Okay, and then in this case, when I'm storing the metadata into the database and generating the thumbnail, I probably could also do this in parallel, right? So in JavaScript, I would do something a little bit like this. So promise all, and then I would make the call to this line right here. And then also I would make the call to this line right here. And essentially what this does is I'm executing each one of the function, and then only after I got result from both, after both promises are resolved, only then I would continue on. So this is kind of like the code that most likely we're going to write, right? If we are building things in a monolithic kind of way, where I have a single server running Node.js, write all this stuff up, pull in the dependency, and then this code coordinates every single step of the way. Now, unfortunately, like you pointed out before, Angela, each one of these lines, right, the extractions and the recognized picture, right now it is all running on a single machine, on a single process. But in a distributed system, in a microservice kind of approach, most likely every single one of those are only web service calls, and the extraction could happen in a smaller machine somewhere else, or in a container running on Amazon Elastic Container Service or Elastic Kubernetes Service. All these processes could be running in small little containers, and therefore, in a typical distributed system fashion, we want to design for failure, right? So every single step of the way, extraction could fail. The recognizing the picture could fail, the storing to our data store could fail, and we probably want to have that logging, error handling, retries mechanism, and whatnot. So even though right now it's looking fairly clean, I think as a developer I would be fairly okay with this code, but I need to kind of make it a little bit more robust. So let's say one way of doing that is in this case where, let me just go to the recognize function right here, I would probably have something like, this, right? So if I call recognize picture and it's successful, then this should execute. But if there's an error, I will need to do something else. And this is where it gets tricky, because like I said before, I probably want to do some logging. I want to do some retry. I want to retry the retry, right? Keep on retrying. At some point, I need to give up so that I don't introduce, a denial of service attack to the downstream services. I probably also have to do exponential fallback, right? I need to make sure that if I retry the next second, I probably would want to wait longer if the service is still failing. Maybe I'll wait until 2 seconds, 4 seconds, 8 seconds, such that I don't introduce, even more loads on the services that are having issues. And then, many other concerns, right? Maybe even, put things into dead letter queue or something, if I can't seem to process the message. So there's a bunch of stuff here. Now, to make things worse, every single one of these lines, like metadata store and generate thumbnail and extraction, may have a slightly different policy, right? Different sets of compensating transaction. In the case of, recognizing picture, maybe you don't have to do any compensating transaction. But in the case of a database store, you might want to roll back certain things. So this error handling code will probably need to happen in every single line where we're making a call outside the process. So I probably would have something like that here. I would have something like that here, and it just kind of complicates a little bit. Now, is there anything that you think I can improve on this piece of code, Angela?
Yeah, so great question. So as I think back to my software engineering days, I spent maybe 90% of the time on actually handling errors rather than writing the code for the happy case. And so given the complexity with all the different things that can go wrong in your application, when you break a monolith application into a distributed microservices model where each microservice can fail in its own ways, and as Ron pointed out, based on the kind of error you get, you would make different decisions of what to retry, what to roll back, how many times you retry, and maybe for certain use cases you send user notification, in other cases you put things in your dead later queue. Your code will get more and more complicated as you try to think of all the ways that your different microservices could fail, and you want to make your code reliable. And so this is where step functions, that's what it's designed for, is to make a lot of this a lot easier. And before I dive into showing you what step functions looks like, I made a diagram to kind of give you a sense of, when you think about step functions, where it fits in the application architecture. So when we talk about distributed microservices, kind of an inevitable question comes up is, how do you put the coordination logic? Where do you put it? There are a few options that we can consider. So the first one is very simple. It's on this client. You can put this coordination logic on the client side. So say if you're developing a mobile or web application, it's normal to put a lot of the code of calling different API services on the client itself. The benefit of this is you can do a good reactive experience for the user. So maybe if one of the services fail, you can still display the results from the other services and have a graceful degradation for the user. But the downside of this approach is it doesn't work for every single use case. Sometimes you don't want to expose the internal interfaces between your backend services to external clients.
So just to kind of, make sure that people are following there, we are talking about, let's say, if you have a web application, maybe the shopping cart functionality is driven by service A, the catalog functionality is driven by service B, such that if the shopping cart system are having issues, there's nothing stopping the user from still browsing the catalog and having a look at the details, because they are independent services that are consumed, aggregated by your React app, Vue app, or Angular app, right?
Yeah, that's exactly right. Now, so that's one way of coordinating different microservices, is kind of the brain of what services call happens on the client side. Another very common and awesome architecture is actually a more pub-sub model. In this case, let's say if you're processing orders from your users, you could have service A process the order, make some database calls. Once it's done, send the results to a message bus. The message bus might be implemented using SQS or SNS topics. Once that message gets to the event bus, then you can have additional services subscribe to those events, and that it will take those events and then process the next stage for the user. Maybe in this case, it's calling your fulfillment center to trigger the actual shipping of the products, and another service that does billing for the user. All these different services could then publish events once that's finished, and the subsequent service can pick up events from there.
Yeah, this is the classic microservices kind of implementation where service A, service B, service C are done by separate teams. Many of you probably have heard about this ethos of a two pizza team at Amazon, right? So each one of the team hopefully can only be fed by two pizzas. We've got like small agile kind of team, and each one of those team has the service, owns the operational excellence of the service, and then the way the service A and service B and service C talks to one another hopefully is very loosely coupled in such a way that you can kind of deploy and improve on your service independently. In this case, you're relying on a mediator, an event bus-like thing to coordinate those, or to choreograph those sequences.
Yeah, so there's lots of benefits to this approach. However, when you're just starting to break up your monolith to distribute microservices, there's lots of complexity with this pub-sub model. If you have complex logic, like for example, service C depends on service B and service E happening at the same time and joining the results, or you have branching logic, you have, and when there's different errors, as we talked about, you have to kind of have conditional branching logic based on what the error is. Another thing is when something wrong happens with a message that gets processed through this chain of events, maybe the message got lost or maybe got mishandled. And to be able to troubleshoot, it takes a lot of complexity because there's not a single place where the processing logic happens. Everything is distributed to each component. So it can be very complex to understand what's going on when you have 10 teams all publishing messages to each other, and you're trying to figure out what went wrong at what stage.
Yeah, I can imagine, like especially when you're starting out, right? Like in many cases, you start one single team, maybe decides to create a couple of microservices, and suddenly you have this kind of extra overhead that one needs to do to just kind of make sure that the microservices are chained the right way.
Exactly. So that's why when you're just starting out, there's another great option for coordinating your microservices and placing the logic of the the orchestration, which is to have a centralized orchestrator model. And this will be something happen on the server side where it's in charge of making sure calling service A and calling service B and C at the same time, joining the results, passing on to the next service. So in this model, because the entire processing logic is centralized in one place, it's very easy to reason about. The complexity is lower than a pubset model. And when you try to think about how to implement a central orchestrator kind of architecture, you could, for example, put all those coordination logic in your Node.js or Java code itself. Or the other approach is to offload it to a workflow orchestration engine like Step Functions. And the benefit of using something like Step Functions is, first of all, you get all the coordination framework abstracted away from your actual business logic of A happens before B, C happens after A and B. So you can define your topology of your workflow independent of actually implementing the code to make these service calls. Step Function itself is also a serverless service, which means you don't have to manage any servers that would be running this orchestration logic. It will be in charge of maintaining state, making sure the orchestrator is highly available, the data that's being passed between services are durably stored, so all that good stuff.
So Angela, I've got a question here. So one is, can I avoid server-side orchestration completely? Because, the nice thing about the client-side orchestration is that graceful degradation, right? Like if one service goes down, you're not impacted. Other parts of the site just kind of lights up and people can still use it. Can I just avoid having a server-side, coordinator or orchestrator altogether?
So what would be the alternative?
Just calling everything from the client side.
Yeah, so the one problem with calling everything from the client side is you don't always necessarily want to externalize all your backend services. So in some example, maybe you have API that you're exposing to a third-party partner. You don't necessarily want them to have all the access to individual backend service logic that make up your microservice.
Yeah.
So you want to shield that away from your client. Other times you might just want to provide a simple service so that the client doesn't have to worry about how it works internally. It also is a concept of encapsulation so that for the client, all it knows is I'm talking to an image processing service. It does all the things I need it to do, and I just get a result at the end of it. So
got it. Okay.
Definitely use cases for both client-side and serverless orchestration.
And I can imagine how in our shopping cart, e-commerce website scenario, you probably don't want to expose your inventory shipping service, right, without going through a payment gateway step beforehand.
Yeah, that's a great.
Okay, that makes sense. Now, I guess the code that I wrote, that Node.js JavaScript app, it's kind of similar to the orchestrator kind of pattern, right? Where this piece of code, right, really is keeping track of all the different promises or all the different asynchronous calls to each one of the potential web services.
Yeah, so in this Step Functions world, you can actually convert all this orchestration logic from code into the Step Functions state language, which is a JSON way of basically defining these sequences of steps that make up your application logic. So to make it more understandable, let me take you to the Step Functions console. And we can actually take a look at the state machine, which is basically a blueprint or a template of where you define the steps that make up your application workflow. And here's an example of image processing workflow that kind of mirrors what we just saw in the Node.js application. So on the left-hand side, you can see the JSON definition of the various steps that make up this image processing procedure. On the right-hand side, you can actually get a diagram generated from the JSON definition, which is, again, another plus of using step functions is you get this visualization out of the box to help you understand and visualize what's happening with and how your different microservices are communicating and triggering one another. So as you can see here, we'll start with maybe the extract metadata stage. We can have conditional logic that does a input validation check of whether the image type is a supported model, just like what we did here in our validator code. We can have additional steps to transform the metadata to call recognition, generate thumbnail, and things could happen in parallel. And after all this processing is done, we can index all the metadata we extracted into a database. So
we've got a question, Angela. Someone is wondering, that diagram looks kind of neat, right? Especially for documentation purposes. Is there a way to export that out? You know, the diagram that it generates?
Yeah, great question. So at this point, the step functions service, the only way to access the diagram is by going to the console. We've heard of some customers that actually uses a headless browser in a Lambda function to actually take a screenshot of the diagram. So that's one way of going about it. The other way is just to really go to the step functions console and take a look at the visualization from there.
Yeah.
You can actually make it even. You can zoom in, zoom out. Especially, it comes really handy when you actually have a huge diagram with many steps. I've seen step functions with hundreds of steps, so it can get really complex, and the visualization really help you to understand what's going on.
Yeah, exciting. That's a potential cool JavaScript project, I think, to just make that functionality as a library that people can leverage. That'd be cool, I think.
Yeah, if somebody listening wants to put that as a project onto the serverless app repo, that would be an awesome add to the step functions user community. So let me show you an example of actually kicking off one of these image processing workflows. So in order to start the execution of a given workflow, we need to give it some input payloads. So in our case, since we're processing images and the images are stored on S3, what we need is the S3 bucket and the key name of the image. So let me copy from my editor over here. And you can actually specify execution ID, and you can also leave that out. If you leave that out, the step functions service will automatically generate an ID for you, so you can track a specific execution for a specific input that you pass in. So get this started. And it's really cool because everything here is color coded, so you can see which step is actually in progress. You can actually watch this state machine progress throughout this workflow. It looks like everything just finished successfully with all the green lighting up. Another cool thing of this visualization is also when you have branching logic, so for some cases, maybe depending on the input, you might take a different execution path. This visualization can help you see which execution path it took. If there's error that happened, that state will be marked as the failed state, and you can see it's marked as red. And if you click on the individual state, of that is failed or succeeded, you can take a look at what are the exact input that got passed into this step, what was the output of this step, and if there was any exceptions, you can also look at it here. So it's very handy when you're developing applications. Makes it a lot simpler than if you were to do everything in a huge monolithic application.
So for those who just joined, what Angela is showing here is AWS Step Functions, and really we're kind of showing an alternative implementation to the very rudimentary Node.js code that I wrote to coordinate all these various little steps. Angela, so earlier on when we just kind of started, we had questions around monolithic lambdas, and essentially what we're saying is, what if that piece of code that I wrote, right, that calls extraction of the image metadata, doing the image type check, and then sending the web service call to recognition, waiting for it, and all that is encapsulated in a lambda? That's kind of still serverless, right? What would be the benefit of going down that monolithic lambda approach versus using step functions to coordinate all these calls?
Yeah, so with if you were to put all that coordination logic inside the Lambda function, if it's fairly simple logic, like I could see it being, if it's a manageable amount of logic, it's totally doable. But there's a few more benefits if you were to kind of move to a more distributed model with step functions. So first of all, the code that's doing the coordination now doesn't live in a Lambda function, which means you're not paying for the time that it's executing. So when you think about a piece of coordination logic, most of the time it's just sending out a request and waiting for the response. So the code itself is not really doing much, and it's really just sitting idle, firing off requests and waiting for responses. So one of the benefits you get is kind of the cost savings of not having something that's just sitting there to make requests and waiting. The other benefit is really, as we will see later on, each of these steps, you can configure by using a few lines of JSON configuration. You can configure things like exponential retry. You can configure error caching logic as part of the topology of your workflow. This makes it much simpler to deal with things like error handling and retries compared to if you were to write everything inside the code itself, because every step can have its own way of failing, and your code will get a lot more complex if you have 10 steps. Each step could have 10 different ways of failing.
Yeah, and I guess just to add on that, I can imagine that if these steps took or takes less than 5 minutes, then it fits into the maximum runtime of an AWS Lambda function, right? You could do it that way, but in this case, obviously, you are not constrained of an overall 5 minutes duration, right? You can span much longer. I would imagine probably even days or months or however you like it to be.
Yeah, so that's another great thing about step functions. So each execution can span up to a year for execution time. So we have customers that leverage step functions for a mix of maybe human type of tasks along with automated tasks that are performed by computers. And so this is not limited to coordinating services that are made up of Lambda functions, as well as long-running tasks or things that are waiting for a human input, like a human wants to approve a certain stage before you move on to the next.
Now, so, the state progression, the state of these executions, is that durable in a sense that my piece of code, right? If if we're still waiting on a result from one of the web service, and then for one reason or another, that machine went down, right, loses connectivity or whatever that may be, then suddenly we have to retry the whole thing. We have to start from step one again because we're not storing the state of the executions anywhere. With step functions, is every single step progression, persisted into a durable store?
Yeah, so definitely every single step, as we can see here, the input and outputs, and for each execution where it is currently at in the workflow, all of those state is durably stored and checkpointed by the step function service. If you're familiar with the Amazon availability zone and region model, so all of this data is stored across multiple availability zones. So even if one of these services would fail, or even if one of the servers in the backend fail, all of those state is stored in across availability zones, which means any service can pick up where it left off and continue with the execution. So going back to this example execution we just showed, in the Step Functions console, you can actually also see the entire event history of how long did each step took, and it also helps you to figure out if one of my workflows is taking a long time, where in this workflow did the bottleneck come from. You can see the state transition happens between each step. So very handy as you're trying to kind of operationalize, monitor, and look at, for every input that went into my system, what are the different steps it took, and if there's errors, where the error happened, and where are the details. So it's all very easily identifiable in the UI itself. Now, all of this information is also available through the Step Functions API, so you can also export it to your favorite log monitoring or analytics platform that you like as well.
Awesome. Now, can you show me how I can, potentially convert all my JavaScript code into a step function orchestrator?
Yeah, so let's get started converting our code from this into something that looks like this in Step Functions. Now, to get started, we can create a new state machine in the Step Function console itself. And so if you look here, there's a few options for help you getting started. You can pick one of the templates that gets you started quickly. So it has some of the different constructs examples built in. So for us to get started, let's start with a hello world example. And when you create a Step Functions using the console, so we need to give it a name. So let's call this Twitch Breaking Monolith. You will also need the IAM role. So this is the role that's used by the Step Function service in order to invoke Lambda functions on your behalf. So I created one right before this episode called State Machine Role US East 1. And if you're interested in kind of seeing what this role is actually made of or what are the permissions associated with it, this is actually created using CloudFormation. So we have all of our...
You can click on text editor, yeah. View text editor, ACE.
Yeah. Thanks for the help. So this is a CloudFormation template that we define the IAM role with. As you can see here, the permissions for this role is to invoke any Lambda functions, and the assume role policy here is for the state machine or Step Function service to be able to assume this role to invoke Lambda functions.
Yeah, and for those who are new to AWS, essentially IAM is the security construct for all the different resources within AWS, what it can and cannot do. So in this case, we're granting permission for our step functions to invoke any Lambda functions, but in your case, probably you want to limit it to specific ones that you're using.
Yeah, so let's get started with kind of drafting our first state machine definition. So as you can see here, it's pretty straightforward JSON. For comments, let's give it something descriptive about what this workflow will do. Let's call it image processing workflow. And then the bulk of the state machine definition is actually listing the different steps that make up your application. So in this example, let's start with our first step, which is extract image metadata. So every step has a unique name within the state machine, so that's how you can reference which states connect to which subsequent stage. And you'll see here also we have a start at node. This is basically a pointer that tells Step Functions where's the starting point, which is the first step that the execution engine should start with. And as you make changes in this editor, you can actually click the refresh button here to actually visualize what you're typing on the left to make sure that it's what you expected the flow to be on the right-hand side in the visualization section. So for every state that you create in state machine in Step Functions, there's a type associated with it. So the state language is very much similar to kind of a rich featured programming language with constructs like conditional logic. It has things like forking and joining. It has things like error retry handling, try catch, finally type of logic. And so this pass type we're using here is basically a way for you to mock or stub a particular step. So before you actually implement this with the actual code that does the image extraction, we can actually stub out this particular step so we can formulate the structure of our workflow without having to actually do the implementation. When I talk to customers, they also find this feature super helpful when you have a team of engineers that want to implement different parts of your workflow. First, define the individual steps that make up this workflow, and once you define the different steps and the interfaces between each step, you can easily just give your developers sprint tasks to actually implement the individual steps later. So it's a great way kind of to also make your team more easily make your team collaborate more easily by leveraging Step Functions. So once we have a past
pro tip number one, use past states for mocking states, right? That's pretty cool.
Yeah, exactly. So when you actually do a stub or mock past state, you can actually also dictate the output that will be generated by this particular past state. So in this case, since we're extracting image metadata, let's give it a example output to be able to tell us, after this state that we got some information about this image, maybe we extracted the format to be JPEG. And the last piece that's always present in every state's definition is either a marker that says this is the end of your state machine execution, or if there's subsequent steps to it, pointer to the next step. So at this point, let's just create a single state machine with a single step, and everything looks good on the right. So let's create our state machine. So once you create a state machine, you can immediately start testing it out. Since that we only have a mock state in our definition right now, we can actually just test it with empty input. As you can see here, we gave the input to be empty JSON, and we can see the output that is generated after this workflow has passed through the state we defined. Now that we have a structure for a single state here, Ron, can you help us convert our first part of our application into a Lambda function?
Of course, because you need that as a Lambda function to execute on, right? So let's switch back to Cloud9. And I'm going to, so if you notice, we are working on the top left folder, 00 Twitch Live. I'm going to go into that folder, if you don't mind expanding the bash window, Angela, so you can see it. Okay, all right, so I'm going to, where are we now? We are in environment, so I'm going to go into the Twitch Live folder, and this is indeed our folder there. I'm going to create a new Lambda application or a Lambda function. I'm just going to use SAM init runtime, and I'm going to use Node.js 8.10. For those of you who are new to SAM is a collection of features and functionality available on GitHub, AWS Serverless Application Model. It has a lot of cool features, including the CLI capability to just kind of, easily start a new application and define your functions and whatnot. So now I have the SAM app on the folder, and one of the function that's created is called Hello World. So I'm going to rename the Hello World to our function called extract metadata. On the app, I'm going to, it has a boilerplate code here. And for those of you who are new to Lambda, essentially what it does is, every time the Lambda function is triggered by something, it will execute the code, this code right here, right? So in this case, it's making a web service call to Axios, but it could be anything. And the way in which you pass on parameters are through the event object or context object. And once it's finished, you're expected to, call the callback function there. And because it's Node.js 8.10, you see also the asynchronous keyword there. But just for simplicity, we're going to remain using promises. So in this case, like we said earlier, we want to convert our extract metadata function into Lambda handler. So we are going to just simply do this. We're going to first import the metadata, which is metadata required. It is one folder down, no, two folders down. So extract metadata, SAM app, and then go to lib, and then metadata. So that's the right place. And then I could then do this, var metadata. Hold on. So this needs to be the same promises code, right? Which is kind of look a little bit like this. Metadata, extract the image, and then once I'm done, I'm going to get the file metadata back, the extracted metadata. And then I'm going to pass on the result into my callback. And the callback takes two parameters. One is if there's an error, and there's no error, it's null. And I'm going to pass on the object itself. Now at this point, I don't have the image, right? So I'm going to get the image from the event object. And in this case, I'm going to get it from src key. And just gonna construct another JSON object here, and src bucket. That's kind of it. right? So in essence here, I'm getting all the parameters from this object, key and bucket, and then I'm going to pass on this image reference into my metadata extract. Just to make sure that it's packaged correctly and all that, I'm going to copy across the library function into our extract metadata here, just to make sure that it is referenced properly, so it doesn't have to go out from the folder. Right, so it looks kind of a little bit more like this now. And what you notice here is I'm not putting my implementation inside the Lambda function, right? So the implementation of the extraction of the metadata is still pretty much encapsulated in that library, and I'm just kind of making a call to the library function. So once I'm done, I've got it here. If I want to, SAM allows me to test it locally and all that. I think, just for the purpose of the session, I'm just gonna cut it short and I'm just gonna deploy it right away. I'm pretty confident of those changes. So I'm gonna package the. Oh,
hey, well, one thing that one suggestion here is just to keep things consistent. I've been using S3 key and S3 bucket in the Lambda event. So if we can just quickly change this to S3 key.
Absolutely. Thank you. And then if we go to the template.yaml, Angela, I just need to change the name. So the resources, I'm going to call it extract metadata. It should be calling our app.js, and the function is called Lambda handler, Node.js 8.10. We don't need any environment variables. We can just keep it there. We don't need to expose it from API gateway in this case. So I'm just going to remove that. And I'm going to keep the, you know what? I don't need the outputs. I'm just going to keep the name of the ARN and the IAM role. I just want to make sure the name is consistent. All right, something like that.
I'm not seeing the changes you're making, by the way.
Oh.
We're looking at the same file.
Yeah, that is interesting. Let me just continue on. Maybe or if you want to close the file and open it back up again, it'll kick it off.
Reload this file, yes. Okay, now looks great.
Okay, and then where's the IAM role? I think I messed up a little bit. Okay.
So let me also change the code URI to match the file folder name that you renamed here.
Mm-hmm.
Extract. Can't type.
Okay, I think that's pretty much it. So what I've done so far is this is a SAM template file, right? What I'm doing is I'm just declaring the Lambda function, pointing to the code that is in the subfolder, extract metadata. The handler is app.js, the function is Lambda handler, the runtime is Node.js 8.10, and I think that's pretty much it. So I'm going to now go to the console.
I think you also need the permissions here for the Lambda function.
Oh yeah, that's true. That's true. Let's do that. So let's see, what role do we need? So I think I'm just going to use the default role, which kind of looks a little bit like this. Right, so it is essentially just a I don't need.
So if you're watching this, whenever you need kind of to look at a reference of what the SAM template format looks like, you can easily go to GitHub, look up AWS SAM.
I think by default, if you don't specify any roles, it would give you the Lambda trust role by default. So let's just try and see if that works.
So we have lots of examples on the SAM websites.
So just mistype. So now I'm at the console. I'm going to package the YAML file, which is SAM package template.yaml. Oh, am I in the wrong folder? I think I'm in the wrong folder. Yep, template YAML file is there. So now I'm gonna package it up.
Hello world. Looks like we didn't change the code URI. I can make this change right now.
Oh, okay. I thought you did. Maybe I overwritten it.
Okay, package.
Okay. Now I'm just going to deploy it. So now I'm going to call SAM deploy, and I'm going to call the compiled CloudFormation file that SAM already prepared. So in this case, the code is already uploaded to S3, and I'm just gonna call the stack name extract metadata, and the capabilities for CloudFormation is just capability IAM. There's quite a bit of parameters here, but in essence, it's pretty much the same parameters that you will be using for most of the time. Memory size is invalid. Oh, because it's string and not integer. Let me just quickly do that again. So right now, what it's doing is it's going to deploy our Lambda function.
The code URI went back to.
Okay.
You want to try it again?
Absolutely. Deploy.
It's still saying.
Let's switch to the console and see if it's creating it properly.
Okay, let's go to the CloudFormation console. I'm loading it up right now. Let's create complete.
Yep, successful. So we got it. So we've got the function there.
The Lambda function, Lambda console to take a look at this function that was just launched. We can view the code that we just deployed in the Lambda console here. It looks good.
So now what we've done there is we've taken out a small piece of my original monolithic code base, wrap it inside a Lambda handler, and deploy it as a Lambda function so that now we can call it from our step function.
Yeah, so to make this, looks like it doesn't have the permission to read from S3, so I'm going to make one more change in our SAM template so we can, so the Lambda function will have access to read from S3. So let me just get the syntax from one of the examples on the SAM GitHub page.
Good point.
So instead of SCS, we'll be looking at S3 get object.
Mm-hmm.
Is it objects or objects? Let me check.
Yeah, object.
Resource. Okay, that looks right. We can redeploy our Lambda function using the same commands that Ron just run. That went successfully, and then SAM deploy.
So as you imagine, we probably want to do this for all the other Lambdas, and obviously we don't want you to watch the paint dry with cooking show style. We've deployed all the other ones for you, so we want to make sure that we focus on the step function side of things too.
Yeah, so let's go back and look at the Lambda function. Let me refresh here. Just for sanity, we can check the IAM role that's associated with the Lambda function here. Let's go to the link. Looks like I don't have permission to check.
I can do that. Why don't you go head over to the step function console while I do that, Angela?
Yeah. All right, so now this is the exciting part where we actually hook up our Lambda function with our step functions structure that we have already started with. So let me go to edit this state machine definition. And now since we have a Lambda function that can do metadata extraction for us, I'm going to change the pass type, change the state type from pass to an actual task type. This is the type that will actually allows you to call either a Lambda function or have workers running on EC2 or Docker images on ECS to actually get a piece of work from state machine and perform the task. So this is where the work actually happens, is through the use of a task state. So as you can see here, we get a red because we can no longer just inject the results. What we want is actually have the Lambda function extract the metadata for us. So in order to define what Lambda function this state will be calling, what we need is a resource node here, and it actually has some autocomplete functionality, so we can pick the Lambda function that we just created. Going back, so this Lambda function is called extract metadata, blah, blah, blah. So let me look for that in our autocomplete dropdown. It looks like this one. So this is the Lambda function that we just deployed through CloudFormation and SAM. So refresh the relation here, everything looks good. And let's do a save. And now we're ready to test out our state machine with this single Lambda state that makes up our workflow.
We may have to revert to our cooking show hidden in the oven Lambda function, Angela, because I think I forgot to include a few packages inside the extract metadata. Because extract metadata relies on image magic, I will need to do a few more steps to package up that Lambda. So do you want to, so that we don't get held up on this one, do you want to revert to using the Lambda that's hidden in the oven?
Yeah, let's do that. Just to save some time for our users. Basically, what we would have done to include those packages is basically using npm to install those dependencies into the same directory here and repackage our Lambda function to redeploy. To save you time from actually seeing us redeploy the Lambda function, I'm just going to edit this to use one of the Lambda functions that we already created. That's that we know is working properly. So let me pick this one here and save. Okay, now we have this state machine defined. Let's re-kick off this state machine and let's see what it comes back. Okay, now we get a green execution. So if we look at the output of this state, we see lots of different metadata being extracted using the image magic library. We included in our Lambda function things like resolution, formatting, size, image statistics, EXIF information like geo coordinates, all the good stuff here. So
you might want to slow down on the scrolling, Angela.
Okay, now we have a basic step function with a single Lambda step. We can look at exporting more of the logic from our Node.js application into our step functions. So one of the key things we talked about, the benefit of now, if we go back to look at the metadata extraction library, we'll notice for a certain kind of inputs, it will actually throw an error called image identify error. Now, this is the error type that gets thrown when the image magic library encounters a file type that it cannot recognize. And so in this case, if we think back to our application, we want to be able to reject this image and stop the further processing. And maybe in this case, we want to handle the error, show the user a notification, and maybe we want to clean up the image or the file that can be processed in S3. So let's see how we can do error catching inside in our step functions. So in order to add the error catching logic, let me show you this page, which is the Amazon state language spec that gives you a complete documentation on all the different constructs supported by the state language, from the different type of states to the different error handling constructs. So in this case, let's dive into the error handling section. And if we look at some of these examples here, so here's a good demonstration of how you would define error handling try catch, retry logic for one of your states that make up the state machine. So we see here a catch segment where you can call different error types, and you can say if error equals this error or this other error, you can say then instead of going down the normal execution path, you can actually branch off to, let's say, a specific state that you built for error handling. And so this is what we're going to do for our image identify error. So let me copy this over here and go back to our definition.
So this goes back to a question that was asked maybe about 15 minutes before. How would you know about all the properties of all the syntax in this JSON to tell step functions what to do? And I think that website, that resource, I've just pasted on Twitch on the chat window too. There's the statelanguage.net/spec.html gives you a lot of the all the different syntax, but also a lot of different examples. So in many different cases, it's as simple as just copying and pasting things and tweaking it for your exact kind of purpose.
Yeah, thanks for that, Ron. And so as we can see here, now our use case is if we encounter this particular error that we define in the Lambda function, we can actually catch the specific error and handle it in our state machine. So in this case, we're going to have a different state specifically for handling the error. And we can also make this into a mock placeholder state. And we can say here, the error successfully handled. And this is also an end state. So if we branch into this segment, this will also terminate the state machine execution. Now we need to point our catch clause to use that state when we encounter this specific error. So when I refresh the page, you can see here. So in a normal situation, when we get to this metadata stage, there's a typo I just noticed. We will directly go to finish the state machine, and if we encounter this specific error, we can have a specific error handler for this this image type error. So let me save this, and we can test this out. So first, let me try a file that I uploaded to our S3 bucket. That's actually a txt file, but I mistakenly saved it as a JPEG extension. So the user might have a false file that they think are image, but actually are not. So to simulate that, we have this test input right here. I'm going to try it out here. And as you can see, the error got caught by this error handler here, and this second error handling state got invoked. And if we go back to try a actual normal image, we should be able to see this execution go directly to finish without getting caught in the error handling stage.
That's cool.
So just 2 lines of code, you can catch different errors for different types of errors and have different handling logic based on it. Another part of error handling is to do retries for certain errors that, for example, are transient errors or things like maybe you got throttled by the Lambda service. Those are type of scenarios you want to implement exponential retry. And the best way to do that is also using this retry phrase here. And as you can see, we have different parameters you can configure for your retry logics. You can define for your exponential retry the initial wait state, the wait time before you retry again, the backoff exponential component, the rate, and the number of max attempts. So let me copy this over here to back to our state machine. So in this scenario, what we want to do is, for the case of this image identify error, we don't want to do any retries. We want to directly go to the catch phase. And for any other error that we don't expect, we're going to retry up to 3 times. So what we can do is we can define for the image identifier error, we're going to say max attempts 0. So it will not be retried if we encounter this error. For any other use case, which we have a catch-all phrase called states.all, we're going to retry for up to 3 times.
So just to kind of pause on this and seeing what we're doing here. Essentially, we're invoking a Lambda function, right? Extract image metadata. The Lambda function throws an error, throws an exception when it finds a specific kind of case. In this case, if the file type is not of certain type, right? And then we're basically matching the exception name with in step function and decide which path or what we want to do next based on that exception.
That's right. And we also have a try, catch, finally type of scenario where if it's any other error type that gets thrown by the Lambda function or something happened with the Lambda function execution, we can do exponential retry for any other type of errors.
So states.all, I'm guessing it's a magic keyword that step function knows that this is for everything else, right?
Yeah, so exactly. So when you have a more specific error type, it will when the state machine engine runs, it will first try to match the more specific error. In this case, the image identifier error. And if this if the error type didn't match this error, then it will match the states.all catch all magic word. And if you want to see kind of what all the magic words step function supports, it's also defined in our state language spec page. So
yeah, this is really cool, Angela. But in the real world, obviously, every single step probably relies on different types of inputs, or maybe there's even some translation that needs to happen. In the subsequent step, when we're extracting the metadata, my recognition function, right, my deep learning recognition step doesn't need, GPS coordinates. It just needs the images. What can we do here to kind of translate from one input and output to the next so that we can make sure that we're passing the right inputs to the subsequent steps?
Yeah, great question. So step functions actually have a really handy feature for you to do some processing of the payloads when you pass the payload between one step to the next subsequent step. To make it easier for you to understand, I actually drew out some diagrams here as well. So the feature that we're talking about is referred to in step functions as input and output processing. So the idea is usually you have a state, you have inputs, and the state itself generates some outputs. What the input and outputs processing feature of step functions allow you to do is to define different filters and operations on these inputs and outputs, so you can manipulate them to match what the actual microservices require or produces. Now, so to answer your question, so for example, one of my microservices for image recognition, for example, it doesn't need to know about the output of some of my previous steps of the GPS coordinates or other additional info that we extracted earlier. And so what we can do is leverage the feature called input path, which is a way to filter out certain nodes of the JSON payload so that only that part of the JSON payload gets actually passed into the Lambda function that calls recognition. So to visualize this a little bit better, so say that our original input to the state was going to be this JSON document here. We have two fields, RSVP and timestamp. By default, if you don't specify the input path parameter for your state, it will default to $, which is a common JSON path expression that basically is a selector to select the entire JSON. So when you have a $, or a default input path, what this will do is pass the entire JSON payload into the state. Alternatively, you can use the JSON path, which is a common way of specifying a particular node within a JSON document by using a $dot syntax to say, oh, I actually only need the node that's referenced by the ASCII key part of this JSON. So when you specify the input path at $.s3 key, what end up getting passed into the state is just the value of the S3 key. So this is really helpful when you think about there might be different interfaces for your microservice that you want to keep consistent, but sometimes the output of a previous step might not match exactly the input of the next step. And so this is one way you can actually filter out only the part that's required by a particular state and only pass that into your that particular processing step. It also kind of keeps your code and logic clean because now by limiting the amount of information that one of your step has access to, you can avoid kind of building dependencies of things that your code shouldn't be relied upon just because it has the access to those data.
Yeah. And I guess planning this out is important, right? This is almost kind of like, what is the contract of your microservice such that, you know, you can create a robust, reusable microservices?
Yeah, that's exactly right. So since we're on the topic of input path, another really useful feature is the result path feature that happens to process the output of a particular state. Now let's continue our example with this input path here. So we have the state that say produces this output type.png. Type is PNG, and if we use a default configuration, which again is a $, what we'll get is for the output of this entire state is going to just be the output of, say, our Lambda function. Sometimes, or most of the time actually, when I write state machines, I find it extremely helpful if I can not only get the output of my Lambda function to be passed on to my next processing step, but also to get the original input that was passed into my first Lambda function. So in this case, for example, my future processing steps not only wants to know that the type of the image is PNG, but it also wants to know the S3 bucket and S3P that was passed in the beginning as the payload for this state machine. So what you can do is leverage result path. And if you specify $metadata, for example, what this will do is to actually have a joining of your JSON to join the original input with the output that was produced by your Lambda function. And the name of that output portion of your output will be defined by your result path. So in this case, we called it $metadata, and you can see the metadata field here in our eventual output to include the output of the Lambda function.
That makes sense.
Great. So yeah, we can actually do this in our state machine definition as well. So let me quickly add this to our definition, and you can see it happen in action. So result path, let's call this extracted metadata. And we can click save. So now if we start a new execution with our image, once this finish executing right now, if we click on the state, we'll notice now we saw in the output of the state, not only we have the extracted metadata as its own JSON node in our output payload, we also see the original inputs of the S3 bucket and S3 key. So our further processing steps can take advantage of both these information that are available for further processing.
Awesome.
So for the
Sorry, go on.
So in the interest of time, I won't be showing you writing the state machine definition for every step along this application. So let me just quickly show you kind of the end result of after we defined our entire flow, what that looks like, and walk you through the final output, and you can kind of see how this is all put together.
Yeah, I was about to say, let's take the time machine out and fast forward so you can kind of discuss some of the cool features here. But one thing to point out, I guess, what we're doing so far is kind of like take a step-by-step approach, right? So we built the step function, built the Lambda, hook it up, introduce error handling and retries and all that. But in reality, I think most of the time, what I find myself doing is I would model everything using past states. I would deploy all the Lambda in one go, or hopefully you already have those Lambda functions, and then start hooking it up that way. And it just feels a little bit faster. And then the retries and catch, obviously something that you can kind of tweak along the way, because there's nothing stopping you from thinking through just the standard use cases, modeling it out, testing it out, making sure everything is working, and then thinking through from an operational standpoint, how many retries, what are the policies as the next subsequent step. Angela, I've got a great question here. We mentioned before about microservice reuse. How do we avoid the potential pitfall of you change one thing and you break essentially everything, right? So for example, if I want to roll out a new extract image metadata and I needed to introduce some changes in the contract, maybe renaming the inputs or renaming the outputs. Any tips there? I've got a couple of in my mind, but I thought you probably also have opinions on this.
Yeah, I'd love to hear what your thoughts are. For me, when I think about keeping the compatibility when you push out different versions of your code in this paradigm of a combination of Lambda functions and step functions, usually the recommendation, I think it's more actually general applicable, is try your best to make things backward compatible. So let's say so the easiest case is you're introducing a new field and your other consumers can just ignore that new field. And so that's kind of the best case. If you can make things backward compatible, then that makes it a lot easier for the subsequent steps to follow. And if you're making a change that is not backward compatible, thinking of doing it in phases, so that for every change you push, think about the order of how you deploy them, so that you always make sure the consumer of your API can take both the old and the new version of your event format before you actually change the producer of the data. So that would be one way of doing it. The other way of thinking about this is, because everything here is basically infrastructure as code. So the other approach is to just completely create a new stack, basically using a blue-green type of deployment, so that you can actually build a version 2 of all your different components that make up your application. And when you're happy with testing the new version that makes up the new stack, just switch your traffic wholesome to the new version. That way you don't have to think about, this particular component changed, how do I make sure the backward compatibility is there? So that would be my thoughts to that question.
Yeah, no, that makes complete sense. I think what you mentioned before around making the contract of your microservice immutable is an important concept in general, right? Just like microservice best practices. Once you publish a contract, you almost want to, always keep it immutable. If you won't need to publish a new contract, do your best to try and still honor the previous contract. on the Lambda level, obviously there's Lambda versioning, and aliases, and there's a level of abstraction or a layer of indirection there that you can leverage there. You also mentioned about maybe introducing a layer of indirection from a step function standpoint, right? If we're treating a state machine like this, a definition, as immutable, then we can also have multiple versions of a step function. But also keep in mind that, let's say, for example, if you have a long-running step function that spans, days or weeks, once you initiate it, it'll take the definition of the state machine as how you defined it at that point, right? When you have step function version 1 and you are stuck on step 3, and you modify that state machine, we're not going to modify all the state machines that are already in flight. So you have that also kind of level of backward compatibility there.
Yeah, so exactly, that's right. So if you have an in-flight execution for your state machine, even if you change the definition during the process, it won't change what's actually currently in flight. It will only be any new executions that are started after the update will get the updated definition.
Mm-hmm. So with this final state, where we are essentially have converted all my JavaScript code into step functions, and we've extracted out all the different pieces of codes into separate Lambda functions. You're doing a couple of interesting things here. Do you want to take us through a couple of those cool stuff that you're doing, like parallel and concurrent execution and whatnot?
Yeah, definitely. So we've kind of dived a lot onto our first state, where we have a combination of catching different errors, doing retries, but there are also lots of other interesting constructs that you can use to compose your, to model your application logic. So the next state here is we call it choice state, which allows you to have conditional branching logic based on the input. So again, here we're doing a conditional by comparing the extracted metadata of the image to see, is this a JPEG or PNG? If it is, then we can move on to the furthest processing steps. Otherwise, also put that, reject that image into and have the not supported image type state to handle that error. And so we talked about kind of using input path and result path to help you kind of mangle the JSON into a format that's supported by your Lambda function or microservices. But sometimes you need to do a lot more than just simple JSON selecting particular nodes or joining two JSON documents. If you need to do more complex kind of JSON transformations, our recommendation is you can actually do that in one Lambda function, which is what we're doing here. Yeah. So to prepare the payload for the other processing stages into a format that those microservices take, you can actually write a very simple Lambda function. All it does is do some JSON transformation.
Mm-hmm.
So now, once we're prepared our metadata to be consumed by the further microservices, this part is interesting because we're using the parallel state for step functions. So this allows you to, if you have multiple services that don't depend on each other, you can leverage parallelization and run them at the same time. So you can get your results a lot faster than if you're doing it in a procedural fashion. And so this is kind of how you define the multiple branches that make up your parallel processing. And as you can see here, when you define a parallel state, every single branch that that makes up the parallel state itself almost looks like a mini step function. So you can actually nest almost a state machine within the state machine if you were to do a parallel type of workflow. So you can have, for each branch of a parallel state, you can have a starting point, and you can have multiple states that make up that branch, and you will have an end state of that particular branch. And as you can imagine, you can have many of these different branches all happening in parallel.
So far we've been showing the audience, how to start execution from the console. But obviously, in reality, something will call it, and that something is most likely, a API gateway if you're exposing this entire thing as an API or another Lambda function. How would you go about executing this programmatically, Angela?
Yeah, so there's a few different options. So if we go back to our web app example, what we're doing here is actually, as part of uploading the image to S3, we have a event trigger configured on the S3 bucket. So I can show you here. So if we go to the bucket properties panel, we can see an event for the S3 bucket being configured. And this actually triggers a Lambda function that starts a new execution for the state machine by calling the Step Functions API. So that's one approach, is to do kind of an event-driven model where you have a upload or a write to a DynamoDB table trigger event, and that event then can be processed by a Lambda function that then triggers a state machine. Another way to do it is through CloudWatch events. So CloudWatch events is AWS's kind of general event bus of everything that's happening across different services. So one example might be you're creating EBS snapshots for your for your backup purposes, and you can actually trigger a step function state machine that's being triggered by that CloudWatch event that this EBS snapshot has finished, and the step functions can then do multiple things. They can, for example, create a cross-region copy of your EBS snapshot. It can clean up any old snapshots you no longer need, coordinate a complete multi-step process of your IT automation based on different things triggered in your environment using the integration between CloudWatch events and step functions. Then after that, the biggest kind of common use case of triggering step functions actually fronting it with API gateway. So there's also integration between API gateway and step functions. So you can actually call API gateway. You can use your preferred method of authentication and authorization, and allow different external clients to trigger step function executions through a REST API hosted on the API gateway service.
So I just want to make sure that I got that right. So the API gateway use case is probably very common, right? Because we can model lots of this microservice coordination on the server side using step function. But you mentioned before around subscribing events from CloudWatch. I guess I could think of a simple kind of polling mechanics, right? Just like using CloudWatch timer and spinning up step function to do certain things. But what you mentioned before around IT automation or infrastructure automation and using step functions to define those steps, that's kind of cool. That's kind of like a DevOps use case for step functions.
Yeah, so we have lots of reference architectures on our AWS blog. So one of them is actually the process I just described. So if you look for step functions, EBS snapshots, we have a reference architecture that actually shows you using step functions to do the EBS snapshot management process I just described. We also have a different blog post on our website that uses step functions to help you with the deployment traffic shifting control when you actually deploy new code to your Lambda functions. So we can also find that blog post and share it with you on the on our chat window here.
Yeah.
Another cool reference architecture here is one of our community leaders and now AWS colleague as well actually built this Step Functions tool to able to tune your Lambda functions, so you can execute your Lambda function in parallel using memory settings and figure out the best, most optimal memory setting for your Lambda functions. So there's lots of cool things you can do with Step Functions.
I've got another question, Angela. So far, we've been showing modifying our step functions in the console. And there's I can see a lot of benefit to this, right? We've got the syntax highlighting, you've got the autocomplete, even auto-completing the Lambda functions that's available for me. So that's super helpful. I've got the WYSIWYG editor or preview on the right where I can kind of see the model. But in reality, hopefully, people are using CI/CD, continuous integration and continuous deployment server. What we do, we would be probably writing this JSON in our favorite IDE like Cloud9 or any code editor out there on my local machine. I would check it into Git, and then all these things are going to be deployed automatically for me. What's the story there? What can I do to deploy that from a CI/CD pipeline?
Yeah, so great question. So the console itself is perfect when you're just getting started with the service. You want to get an interactive experience, visualizing your state machine on the right-hand side. You can get syntax highlighting. However, in reality, when you're kind of more fluent with the service, you want to do everything in a CI/CD fashion. And so what you can do with Step Functions, being part of your CI/CD and version control pipeline, is to actually use CloudFormation to deploy your Step Functions alongside with the Lambda functions that it's made up of. So we actually have in our documentation page, we have a step-by-step tutorial of showing you how you can set up a CloudFormation template. And we can also walk you through here for a little bit. And so if we go back to the SAM template that we got started with here, we can actually add our same machine into our CloudFormation template, so you can deploy the Lambda functions along with the Step Functions at the same time. So if we go back to this documentation example, here we're defining the Lambda role, then the Lambda function itself. Then we would need this part to define the IAM role used by the Step function itself to call Lambda functions. So we can actually just paste this section here into our CloudFormation/SAM template. So again, here we see the type here is the IAM role. This is the role we're going to reference when we create the Step Functions itself within CloudFormation. So here we can, in our documentation, we actually show an example of how you can define a Step Function state machine within CloudFormation. Let me make this bigger. So you can see here the type of this resource would be Step Function state machine, and you can actually inline the definition string, the JSON definition that we've been working on, into the CloudFormation template itself. Another cool thing here is, remember earlier when we hooked up the Step Functions with the Lambda functions we deployed, that we had to type in the ARN manually as part of the definition. So here, what we can do is instead using a pointer function within the CloudFormation template, so it will automatically replace the Lambda function's placeholder here with the actual Lambda ARN that's generated by the CloudFormation.
Right. So I guess in this case, if your versioning strategy is to have a single CloudFormation that version the step function and all the dependent Lambda functions together, you can then just rely on the string replace, the substitute, to hook all those different pieces together, right? You deploy the Lambda functions, deploy the step functions, and then CloudFormation will also link up all the new function that you just deployed.
Yeah, that's right. So if let's say we copy over this piece of the definition into our CloudFormation, and instead of the placeholder here, we're going to use our actual definition that we just worked on. This is YAML, we have to get the spacing right. And so the placeholder lambda ARN will call our extract metadata lambda function. So the string substitution will match our lambda function.
Right, right.
And so with this, we can actually do another SAM package and SAM deploy.
Yeah, and in this case, we're not just deploying the Lambda, but also deploying the step functions together in a single deployment package. That's super cool. We've got another question, Angela. So, what is the best way to integrate step functions with non-Lambda tasks? So, this specific question is about, let's say running the actual task on a container, but I guess, I can make the question slightly more general. What if my worker is an on-premises workload? It's a Java app running on-premises. What's the story there?
Yeah, so again, that's a great question. So the way that you can actually integrate non-Lambda or non-serverless components into your step functions workflow is very straightforward. So if we go back to our definition, and we talked about having a task state here to actually refer to a Lambda function, so the state machine can call a Lambda function. You can actually, instead of calling a task Lambda function, you can also call what we call an activity task. So activity task is a different type that's supported by the step functions task state that allows you to have a fleet of workers, whether that's on-premise or that's on EC2 or on Docker containers, that can actually pull against this activity. And whenever there's work to do, when the same machine reaches this step, all the workers who's pulling against this activity will get a token that says, oh, here, there's a piece of work for you to do. Here's the image that you need to process. And the workers, once it gets this task token, can process the event on-premise or in the Docker container. Once it's finished, it will you would write your code to report back your results of the processing back to step functions along with the task token. So it identifies which execution you're running against, and the step functions will take that and mark this step as complete and move on to coordinate to the next call.
Yeah, that makes sense. So it's a similar pattern that you would do if you are leveraging things like Amazon SQS, right? Where you have that item in the queue, let your worker pull the particular work items, and once you finish, you say step function, I'm done. Do whatever you need to do next. And then that worker could be hosted anywhere. It doesn't have to be, in AWS even. Maybe it's even your laptop, as long as you have the right permissions and security controls.
Yeah,
Any other
and
things
similar to one more thing to add there. So similar to a Lambda function, you can have retry blocks. You can have error catch. Blocks very similar to for a Lambda function. You can also do that for activity tasks, so you can make sure all your different error cases are handled properly.
Right, and it's really just popping the right work item back in the queue such that hopefully other workers can pick it up.
That's right.
Awesome. So I think we've gone through a lot here, and we're almost using up the entire 2 hours. And thank you so much for the people who have stuck around with us for the last 2 hours. So far we've seen a monolith that I wrote based on Node.js and coordinating a bunch of microservices or coordinating a bunch of code using promises, and then we kind of slowly extract out some of the functionality to Lambda functions and kind of transition across our coordinating code into a step function defined state machine, which is kind of cool. And hopefully that gives some insights to what it takes for you guys to break some of your monolith into a slightly more microservices architecture. I know a couple of our cool customers have gone through the same. Angela, do you have any mentions and interesting stories there?
Yeah, so I'd highly recommend you checking out one of the blog posts written by our customer Yelp. So they actually performed a similar migration from a monolithic application to a more microservice-driven architecture using step functions. And so their story is written here. They talked about pulling their application for subscription account billing process into a step function state machine. So originally they had this batch processing workflow where they look at accounts in batches and process them through a set of servers that they have. And by putting them into step functions, they got a lot better parallelization. So instead of doing a batch workload, they actually started with a step function state machine with just a single state, which is really interesting. And they were able to benefit from even a very simple state machine like this, and eventually breaking it up into further processing steps. And they're continuing to work on breaking their monolithic applications further and have step functions help them with parallelism, help with handling errors and success, different scenarios. So yeah, definitely highly recommend you checking this out, and we can share this link to the Twitch chat window as well.
Yeah, and one of the benefits that I don't think we mentioned before was, all these things are running serverless. So, in the sense that my Node.js application code, all those wasted cycles, right, just waiting for the work to get done, and I'm paying for it. If that's an EC2 machine, I'm paying for a running EC2 machine just to coordinate the work while it's not doing anything on its own. Whereas with step function, it works based on state changes. Now, I think we've got a GitHub repo too, where people can find all the code that you see today. Interesting enough, if you click on the workshops link, it has all the instructions for you to try and go through the step on your own and learn a little bit more about Amazon State Language. So if you're so inclined to reproduce some of the things that we talk about today, please go ahead and check out our Lambda ref architecture image recognition. We're always constantly look for pull requests. So if you have new ideas on how to extend this project, please reach out to us on the GitHub repo. Angela and a lot of the different people at AWS, pay close attention to it. And again, hopefully you enjoyed today's Built on Serverless. I hope we get to see you guys for the next session. Take care.
Thank you.
Angela, are you almost done?